Okay, so this week we'll have a topic of center mass and then we will move on to rotation motion. So moment center of mass is a special point. There is a position of a point. So center mass for any object with reference to any coordinate system is a position vector. It is a position vector. But why is that point important and how do we calculate? Let's first understand significance of center mass. And just imagine you have placed a rod here, which could be a pen also. This is placed on a smooth surface. It is placed, what is surface here? We are looking from the top. So this is a smooth horizontal surface. So you have placed a pen or a rod or any linear object, uniform linear object on a horizontal smooth surface. And if you apply a force here, and I think all of you can easily intuitively think what kind of motion you have. You try on the pen also, what you'll find. So little time later, it may have shape like this, it may have shape like this. So it is this kind of, it will have odd kind of motion. But if I want to understand if this mass of rod was m here, so I have applied force m, mass is m, I should be able to apply laws of motion to this object for this force here. So how do I apply F is equal to ma? Non-particle type object. So far we have taken some cases why we are not able to apply. In this case, not only translation, it is undergoing rotation also. So it is having both the things here. So how do I apply to this case here? And you notice here, this particle has different displacement. This particle has different displacement. So all particles have different displacement. And the fact that they have different displacement implies that their acceleration also have not been same. So when acceleration is not same, how do I apply this equation? So that's a problem in case of what you may call as non-particle object. When we apply Newton's law of motion, the question comes, how do we apply? Is that valid or not valid? And of course, this motion is related to the force here. So different particles have different displacement, has different acceleration. So how to apply laws of motion? What we find here, this is something, though it moves in a random fashion, there is only one particle. In this case, typically if you apply a force, object from rest should have a linear acceleration and linear motion. We find one particle follows laws of motion, which moves in a linear fashion. And what is that point? If I take here, because of symmetry, if I take the midpoint of the rod, even if I'm applying force here, I'll find this midpoint on the rod. If I apply the force, it will, and if we keep the force applied at the same point, we are not removing the force. It's the force acting continuously in same direction, same magnitude. This particle will move in a straight path. And if I consider, rather than taking the whole rod, if I replace the whole rod with one single particle, where should I place the single particle? I place the single particle at center of mass. This whole system, if it is replaced by entire mass, placed at center of mass, and if I apply external forces center of mass, so this particle and will still have some, it will have a certain acceleration, and whatever acceleration this particle is here, the center of mass also will have exactly the same motion. So there's one particle, so it is applicable Newton's law of motion if you have to apply it to an object which is undergoing translation plus rotation. It is only one point will follow that Newton's law of motion. So I can replace whether this entire thing by that object. So, and that point here for different objects, it will have a different thing. If you want to understand, one more way you can think of it, you can imagine that if you take a semicircular ring, you can easily get a semicircular ring. You get a semicircular ring. And what you do here, and semicircular ring, we can throw, the way we can throw a tiny little ball, and we know we throw a ball, it takes a parabolic path. But when we throw this ring here, and half a ring, with circular ring, it doesn't make it not very clear. This will have very odd kind of motion. It will have, it will keep this kind of motion. But if this ring, it has a particular point where center of mass, and we can find, we'll see later, we can easily find the center of mass is at a distance of 2r by pi. So suppose in the ring, suppose what we do here, through some wire, I put a light bulb here at the center of ring, at the center of mass, and I then throw the ring. And this light, this is lit in the dark room. I find this, I will see the light bulb will follow, it will not go this kind of path. It will follow a parabolic path. So here also, there's one point on this extended object which is exactly following the laws of motion as we have understood so far, particle motion, which is that point. Anywhere else I put the light here, if I green light here, if I see the red light here, red light at the center mass, green light at some other point, green light will follow our path. It will not follow a neat parabolic trajectory. But this red bulb, which is placed at the center mass, and is light bulb, so that weight also light, so that it doesn't change the center mass. It will follow that path. So that of there's one more point in terms of importance of center mass. And suppose rather than keeping the rod, had I placed a semicircular ring or any other shape on a horizontal surface, if I apply a force which is something like this, if I apply a force here, important point is this line of action of the force is passing the center mass. If I apply this force, this ring, this semicircular ring also will have pure translation. So the three ways we can understand here, three ways we have defined. One is application of laws of motion. And third, in terms of trajectory, one point only follows the trajectory, which is for particle-like motion. And third thing, if for line of action of a force, if it is passing through center mass, it will move just like a plane translation. Every single particle will have same acceleration, same displacement. So that's why that point is important. So there's a one point on any object, any regular shape object also will have some center mass. So let's find how to go about finding center mass. And to find center mass, there's something called moment of a point. And that term moment will come in the next chapter also, which is the rotation motion. What is, whenever we talk of moment, moment is multiplication of some distance r. Some kind, we kind of say like a r vector. So moment of point mass, when mass is multiplied by r vector, so that also becomes a vector quantity. So let's say suppose there's a point mass m here, and I want to find moment of this mass about origin O. In this reference frame, this point has a coordinate, some xi, yi. In that case, moment of this particular mass will be equal to m cross r, but not m cross r, m into r, because this is scalar quantity, and r being the position vector. So that's what position vector is. So this is r1 is the position vector, and x1 and y1 are coordinate. So moment of this mass is this value. And you know, this value will come as what, if I write in vector form, this value would have come something like this, m into x1 I cap plus m into y1 j cap. See, one quantity is a vector quantity, r vector. So this also will have vector form. And moment anything is vector, we can take two components. So the moment we take is has a I component, it has j component. So moment of mass, that's value of moment of mass is. So what is position of central mass? So once we understand position of central mass, now we are talking about several point mass. If we have several point mass in the space, we'll do for point mass, and then we later on we look at the continuous mass system. So if there are n number of particles, what we do here, central mass is equal to the moment of all masses divided by the total mass. If I calculate for all, if the number of particles, all particles R1, mass M2, position vector R2, if I keep multiplying, this term is sum of moment of all masses divided by the total mass. That equal in terms of if you see in terms of dimension also, it will return a value which is in terms of length. That's called center mass. That's a way to find center mass. And another way to understand is center mass is a point about which sum of the moment of mass is zero. So see, let's understand this part also. Let's see what I mean by next statement here. Suppose we have two masses. One mass is m, other is 2m, and these two masses are at a distance L. To calculate center mass, I can take different coordinate system. If I take this coordinate system here, if I take coordinate system lying at 2m, I'll calculate what is the moment of the first mass. Moment of first mass will be m into L plus m into plus L I cap. So it will be m into L divided by 3m. It will be equal to L by 3. So from here, it will be at a distance L by 3. Okay. And if I check the coordinate system here, I find the center mass will come equal to minus 2L by 3. But though the value of position mass has changed, but it is still pointing to the same point. What if I take the coordinate system at this point itself, where the center mass is? If I take coordinate system at this point here, if I take the coordinate, so I'm calculating the numerator about which point I'm calculating moments about center mass. If I calculate moment about center mass, the position vector should come 0. Center mass and origin apply at the same point. If this has to come 0, it means numerator has to be 0. The sum of the moments of two masses have to be 0. This one is equal to, if this is L, this is equal to 2L by 3, and this is equal to minus L by 3. That's the important point we have to keep in mind. So when I calculate moment about this point, it will be m into 2L by 3 plus m into minus L by 3 is a vector quantity. Still, even though we are taking only x coordinate, so we have to take a sign. So that's another way to understand. That's a point about which sum of moment of all the masses is 0. Okay, so it's same thing if you write in component form, since it's vector quantity, rather RCM, I can write XCM is equal to sum of m into x coordinates, and that's fairly simple. If it is a continuous mass system, what we need to, even though it is continuous, we break into small masses, and each small piece, whether we divide into several small masses, and each mass will have certain position. So we calculate dm into x, add it up, rather than summation. It has summation in form of integration. This is something similar. Mass becomes dm, x remains same, and this is and that's how we calculate center mass. These are, I think, fairly straightforward. No, should not have difficulty. Let's try and understand how do we calculate the center mass from a semicircular ring of radius r. And whenever nothing is mentioned, we have to assume the ring is a uniform ring, unless mentioned otherwise. So what we have done here, we have taken this, we have taken the coordinate at the center. See, we have taken the coordinate system. Origin coincides with the center of circular ring, and this is the axis how it is placed. Now, from symmetry, if I calculate here, a center mass will be a particular point. Since there's a symmetry, and this y-axis is axis of symmetry. Whenever there's axis symmetry, so basically, if I take a certain mass here, there's a corresponding mass here. One has plus x, other has minus x. So whenever I take x component, where the x value when I'm calculating, moments will cancel out. So x coordinate of center mass will come to 0. Or other way of saying, if there's axis of rotation, if there's axis of symmetry, center's mass will lie on the symmetry. Basically, we know x coordinate is 0. Only thing I have to calculate YCM. And this is a continuous one. How would I calculate YCM? This is a YCM will be calculated like this. We again, let's recall what is YCM equal to. I will divide into small pieces. Let's see. So if I divide into several small pieces, and since it is circle, I have defined the position of pieces not in terms of x, define in terms of theta. Let's take one random piece here. One random piece. How do I define this position? This random piece is at an angular position of theta, and it subtends an angle d theta. This is a random piece. What we'll do here, first we'll calculate moment of this piece. Moment of y component, basically y coordinate. So how do I calculate if this mass is dm and this will be is a yi? Okay. So what would be moment of this small mass? So moment of this small mass, basically what you have to calculate YCM, I have to calculate of sum of moment of all mass. I'll calculate moment of one mass and add it up to integration on random mass. Mass per unit length is lambda here. Lambda will be total mass divided by r length. That becomes my lambda term. We have taken a random piece here at theta and theta plus d theta. The y coordinate will be equal to r sine theta, and dm will be equal to lambda into length. Length will equal to rt theta. We have done this kind of thing before. It's really simple. So what is YCM? YCM I'll integrate. I'll calculate sum of the moment of all pieces starting from here, angle 0 to pi. Limits will be from 0 to pi, and this term is dm. This term is y. When I integrate, I divide by total mass, I'll get my YCM. That's a method of calculation, and integration is something we will not do many more. And it comes equal to 1 by pi. And some formula we must memorize. So I'll come to some formula what you need to memorize. So this is something when it was semicircular ring, it is 2r by pi. Let's take a small variation. Suppose a question comes. This is a formula for this, most people remember. So this itself may not come in the examination in this form. See, suppose we have given other thing now. It is given not a semicircular ring, it's a quarter circle, it's a quarter ring. The quarter ring is symmetrically. If I have to find its center of mass and it is placed symmetrical to y-axis, what will be YCM? That's also similar. If it is quarter ring, then basically this angle will become pi by 4, and its YCM will be the limits of integration will change. And other thing you'll notice here, if I take y coordinate of center mass of the left part, Y coordinate of center of mass of the right part also will be same. Okay, calculate center of mass for this part alone, and it will be same as the whole part here. Okay, let's look at some conceptual question. Calculation of center mass is fairly straightforward. It's okay, so let's say an object comprises of a uniform ring of radius r. So this one is a uniform ring we see in dark blue color, and uniform chord AB. So there's some kind of thin rod AB which is placed and which is subtending 90 degree at the center, and not necessarily made of the same material. So mass per unit length here, if this also is a linear object bent in form of a circle, this will have some mass per length, circular ring part, and the rod also has some other mass per unit length. So both lambdas are not same. Mass per unit lengths are not same. Which of the following can be center of mass of the object? So suppose this kind of things are given. So there are few things we can understand for simple example. How do we understand here? There are two parts here. One is circle and one is rod. So whenever we talk about center of mass, entire circle, I can replace with the point mass placed with center of mass. This entire mass of a circle, this becomes mass of a circle, the circular ring. So this entire mass is replaced by this mass here. Where would the center of mass, the rod, be? Basically replacing ring and rod with point mass placed at their center mass. So this way we have placed those two masses at the center mass. If we do so, so whole system is equivalent to 2-point mass system. Moment becomes 2-point mass system, it becomes relatively easy to understand. And what we should know, if there's 2-point mass system, and we can easily find central mass. So suppose I have to find central mass if this is M1 and this is M2. If I take this, had I taken this direction in X dash, very easily can calculate central mass. But what is important point here? This point will lie on the midpoint of the chord. This is a uniform rod. Wherever the center of mass is, it will always lie on the line connecting M1 and M2. It will lie on the line joining M1 and M2, and it cannot be on this side. It will not be on this side. 2-point mass system, center of mass must lie on the line joining, and it will be nearer to the heavy mass. It will be somewhere in between. It cannot be this side or either side. So based on that, we can easily rule out. So first of all, the angle should be 45. These two are x coordinate, y coordinate not equal. This is not possible. They are equal. Okay. But what is the distance of this mass from center? This mass is at a distance of r by root. So first of all, it has to lie on a line which makes 45 degree, and its distance should not be greater than this distance. The distance of center mass from the center cannot be greater than distance of midpoint of the rod. From here, we can easily find out if this comes to be the correct answer. So combined mass must lie on the line joining them and between them. These are concept, and some of them very simple question on finding center mass of combination of shapes. So all those things are fairly simple. All such shapes can be reduced to point mass system. We can, so if there are two shapes here, it becomes equal to 2-point mass. So suppose the square sheet of side L, and there's a semicircular disk of diameter L, so that it just consider this L here, and their mass per unit area is same. So if it is placed like this, where the center of mass will be. So again, saying that so I can replace the whole square with the its entire mass place itself center mass. And similarly, we can find the mass of the disk also and place at the center mass. But for that also, what you should know, you should know the formula. This is simple. Square is of, because symmetry lies at the geometric center. In case of this, we need to remember, in case of semicircular disk, it is equal to 4r by 3 pi. That's the distance of center mass from center here. So if I replace 2-point mass system, moment I replace this 2-point mass system M1 and M2, I can easily find using point mass system formula. So that's a standard method we use to find center of mass for combination of shapes. So what a shape we have, we can replace with equivalent point mass placed at their respective center mass. Okay. Let's look at some more simple application, and this kind of questions are more likely something which require little understanding of question. So there's a thin uniform rod of length L. It's bent at the midpoint at 60 degree. So this rod and bent at the midpoint. So this is 60 degree. Of course, this length also will become L by 2. And other length also is equal to L by 2. And if this is a figure given, as they say, if one side is taken in x-axis, other side is along positive y-axis, what will be the coordinate of center mass if the midpoint is assumed to be origin? So in this case also, see, we can break it down into two parts. One part is this, other part is this, and we can replace two rods now where the point mass placed at the center. So here, if I place here, so this is something rod length is L by 2. So I can replace mass M by 2 placed at the midpoint by 4, 0. That becomes its coordinate. And second one also, the length is L by 2. So I can replace this entire mass with the point mass placed at center mass. And this distance will be L by 4, angle is theta. So x coordinate will be equal to L by 4 cos 60 and y coordinate L by 4 sin 60. So this is the plan. Then I can use these are 2 points on mass system. I can find center mass which will be at the midpoint. I can write again. So I treat this as M1 and M2. I could have written also XC if I have to find XCM. How would I write XCM? M by 2 into x coordinate of this M by 2 into L by 4 plus again M by 2 and L by 4 cos 60 which is equal to into L by 8 and divide by total mass M. Similar way I can find XCM and YCM. That's one way of finding it out. And if you want to understand, just for the sake of understanding things, how we can do in a different way. Another way to do that also, if it is become 2-point mass system, the center of mass will be at the midpoint of joining. So this is where the center of mass will be. And if this is L by 4, the distance of the center mass from here will be equal to root 3 by 2 into L by 4. And this will make an angle of 30 degrees. I can do that also. I can find this length, distance of center mass here, which will be midpoint on the equilateral triangle. After finding with this, once I find this distance here, the center mass will be, this is the distance from center origin here into cos 30 and sin 30 I can find. So they're very simple questions. And coming to some questions where cavity is created. So cavity kind of question and the cavity kind of question may be a little more likely. So let's take a uniform disk and method remains same. All cavity are similar. A uniform disk of radius r is cut from it. So this is a larger disk here. This is the original disk. Let's say this is a radius of 2r here. And from 2r, another cavity of radius r is cut. And this also is as a radius r is cut. And this is a common point of tangency. It means center has to be distance r from the center of an initial disk here. So that their perimeter is touch. What if the what is the position of center mass? How do you find? Just pay attention. This one, all question where something has been cut and removed from a symmetrical mass. So we had original mass for which we knew the center mass, but if something has been cut and removed, it changes. How do we solve such question? This question we have done so many times in different ways. And this part is equal to, so if I call this as A, this is B, and this shape is C. What is A equal to? A is equal to B minus C. So you can understand this minus this is equal to that. So if you have to find center mass, is equal to this minus this. And this mass is, if I take this mass as M, since radius is half, mass becomes M by 4. So this minus this kind of thing is there. So this is equal to, I can, as good as I can take this masses, not plus M by 4 because I have to subtract here. So whenever cavity is there, it becomes like a negative mass because we have to subtract. We have to remove that part, A, B minus C. So figure A is equal to figure B minus C. And when we write XCM here, whenever cavity is created, so I can call this as a full part and this is cut part. So there are two parts. So when we write XCM, so mass of the full part and X coordinate of the full part, and typically used to get plus sign, since it is mass is cut and removed, this part I have to put a minus sign here. So this is minus of the cut part and minus the X coordinate of the cut part divided by the full mass minus the cut part mass. And this part is fairly simple, very easily substitute we can find. So this part is 0 and cut part here is M. You can easily substitute and find an answer. And this comes minus R by 3. What you notice here, if the mass is removed from the right half, center half shifted towards the left hand side. So center mass, if mass is removed, center mass moves in the opposite direction. Center mass is this something, it is initially mass was here. This mass has been cut and removed. It has shifted towards left hand side. Whichever side mass is removed, it shift to other side. Okay. Okay, and so this calculation of center mass is fairly straightforward, and I'll have given some more question in assignment. You can do that. So as we were talking in the beginning, center mass is useful for understanding motion of an object where particle positions are maybe, let's take example. Suppose we take masses M1 and M2. They are connected by spring. If they are connected by spring here, and its initially spring is here unextended. If I apply a force here, we very easily, moment you apply force here, we understand here it will have, this will start getting compressed and the spring length will keep changing. It will have a little complex kind of motion. So this kind of motion, moment we look at two objects separately, we'll see it later, yes, both will execute as such a motion. But it is not so easy to comprehend. But whereas if we take motion of center mass, so basically what we do here, through some magic, there's some magical device which creates a light bulb as the center mass. It gives you center mass at different instances. At all instances, if I know what the center mass is, motion of center mass is easy to understand. So, though individual motion of two masses may not be that easy, the center mass motion is easy. And how do we understand motion of center mass? In that case, this is center mass, this is axiom. So you notice here, this is what axiom was. If we take its derivative, it becomes an equation of VCM, that will be velocity of center mass, rate at which, if both are moving, this becomes velocity of center mass, and it's again derivative, that becomes ACM. So I hope the formula part is fairly simple. Let's look at in terms of motion of center, identical to particle of mass Mi, total mass placed at the center mass, acted upon force external. So if I have to understand how the center of mass will move, if center of mass of which system? M1 plus M2 plus a spring. This whole thing system is taken as one. And we are not looking at internal motion, we are looking only motion of center mass. We have replaced the whole thing with combined mass M1 plus M2 placed at the center mass and acted upon by external force F external. So here internal force will not come into picture. And what we notice here, center mass will have a uniformly accelerated motion. So any point of time, can I find if this is time t is equal to 0, starting from rest, any point of time we can find out what the velocity of center mass will be and what will be the acceleration of center mass. We can find out VCM at any time and we can find out ACM at any time. Only thing what will happen when you find VCM at a particular instance, this will have different velocity V1, this may have a different velocity V2. But again at this instance, if I use this equation and calculate M1 into V1 plus M2 V2 divided by M1 plus M2, it will always match up with this VCM. And similar way, they may have different acceleration at particular point of time. This may have A1 and this may have A2. But if they have A1 and A2, it will always satisfy the condition ACM will be equal to M1 A1. We can take X coordinate separately, say there's only X coordinate, so the bar may not be necessary. M1 A1 plus M2 A2 divided by M1 plus A2 with sign convention. So this is something we can easily find. Their motion will always follow. The velocities of individual particles and accelerations will vary in such a fashion they will always match with the VCM and ACM at the corresponding instance of time. From here we learn a few more things. What happens if external forces are 0? If how do external forces 0, then why would the objects move? Objects move like this. It can be reverse case also. Because suppose these springs are there, the mass is we bring masses, compress them, and suddenly release. Then, as a system, they are not acted upon by any external force. If I take M1 spring and M2 as a system, if initially the spring was compressed and blocks were kept at the two ends, and suddenly we release, both blocks will start moving. But if we take them as a system, their motion will follow this equation. Center of mass motion. So what you notice here is just seeing attention, because many questions are based on application of this. If summation of X component of all forces, we are talking only X component. If I take X component, whatever forces are acting on the system, first of all I am taking only external forces. And after external forces, I resolve into X component and Y component. I take sum of X component. If that comes to 0, it means that there is no net component acting in X direction on a system of particles. Whatever we have taken, it could be 2 particles, 3 particles, it could be multiple objects. The motion of center mass in X direction. See this now, if what happens when the external force is 0? No acceleration, velocity is constant. So in this case, center of motion, the motion of center mass in x direction will be uniform. Okay. What does it mean? So there are two ways we can understand. If net force is zero, what are things we understand here? If net force is zero, if object is in motion, it keeps moving in the same velocity in the same direction. But if the object is at rest, it will continue to remain at rest. Same thing we are saying. If net external force in x direction is zero, so if initially itself the center of mass was having certain velocity, it will continue having same velocity. But if center of mass was at rest, how center of mass was at rest? If both the objects, suppose system consists of only two particles. If both the objects, both the particles were at rest initially, it means center of mass also was at rest. And if the center of mass was initially at rest, internal forces acted, but external force is not acting in x direction, then its x coordinate of center of mass will remain at rest. Its position will not change. So here it will position of center of mass will change at a uniform rate. Here position of center of mass will not change at all. If next, what are two conditions for which it will happen? When does position of center of mass, x coordinate of position of center of mass does not change? When does XCM does not change? Condition, two things have to happen. Net force in x direction has to be zero, and second, initially velocity of center mass has to be at rest. And velocity of center mass can be rest either both the particles have opposite velocity in such a way the velocity of center mass comes to zero, or both are at rest. So when both are at rest, no force is acting, XCM remains unchanged. And 77 questions are based on that also. The position of center mass will not change. So that's example of this motion of center mass. So something like this. So suppose we have compressed string. Okay. Suppose we have M2 has not come. The two masses are there, and spring is compressed. The initial length was something like this L0, and it has been compressed to some distance, and it's then two masses are kept here. What will happen in this case? Suddenly, if we release from compressed state, what does release from compressed state mean? Just before release or soon after release, this velocity is zero, this velocity is zero. If we release from rest, basically both velocities are zero, which implies VCM is zero. When I release it also, at any moment after some time, I find this requires some velocity, this requires some velocity. But whatever velocity they acquire, V1 and V2, VCM will remain zero. And if initial position of center mass was this, later on also at any instance of time, the center mass will remain at the same position. That's the point we are taking here. So even if they start moving due to internal forces, the position of center mass will not change. Two block in a spring as a system. And VCM will remain constant. And this is that's one type of question. Second thing, what we are saying, if external it is zero, motion of sex drive, if VCM is not zero, it will keep moving at a constant velocity. In that case, keep moving the constant velocity, center mass moving velocity. What is this term here? If I write this is VCM term. And what does this term indicate? This term indicate nothing but summation of momentum of all components which are part of the system. So if this term is zero, it means momentum of the system, change in momentum remains zero. X component of momentum system remains constant. If this remains constant, it means momentum remains constant. This is conservation of linear momentum. So let's try and understand what is conservation of linear momentum. When would summation of component of linear momentum in x direction remain constant? Condition for that is not necessarily that force acting on the external force on the system has to be zero. What is the condition required? This is a condition required. Let's understand this condition. It does not say the external force has to be zero. It only says if even if external force are acting is zero, in that case momentum of the system is conserved in all direction. But if external forces are acting, but external forces have net component x direction is zero, even then the momentum in x direction remains constant. That is conservation of momentum condition. And what is projectile trajectory? Projectile trajectory also is a common thing. A projectile explodes in the midair, wherever it need not be highest point. Whichever point a projectile explodes in midair, and explosion basically means the internal forces have acted. And if when the project, then trajectory of central mass remain unchanged. So afterwards, it became 2 particle or 3 particle. But if we, any instance, we think what is the center of mass? Center of mass will coincide with the original trajectory of the projectile. So there are 3 cases. One case, what are the things here? Actually, here axiom remains constant. Here momentum remains constant. And third case is trajectory remains constant. What has happened here? Axiom, when does axiom remain constant here? Axiom, this remains constant when external forces x component is equal to 0, and initially VCM also was 0. Then it remains constant. This is when is this condition? This condition is when only, it doesn't matter what the initial was, this is 0. And what is trajectory case? In trajectory case, external forces are acting, but they are not changing. No change in external forces. If there's no change in external forces, only internal forces are active. So whatever path it was following, it will continue to follow the same path. So these are 3 important applications of center mass when position axiom does not change. So in each cases will deal with a component. Okay, x component, y component separate. Momentum constant and trajectory unchanged. Trajectory unchanged, external force is acting. These 2 cases, external force not acting. Here velocity also 0, here initial velocity not 0. So these are 3 important cases of application of center mass, and majority of questions are related to one of these 3 things. Okay. Yes.
Sir, I didn't understand the part about the projectile trajectory.
Projectile trajectory. Okay. See, projectile trajectory, say, we'll come to some numerical also, we'll understand. Let's see that part. So if I have mass m here, so if mass m have projected here, okay, and it somewhere it's a trajectory. So basically, I call this is time t1, it is here. At time t2, it reaches this point. Time t, it reaches this point, and time capital T, it's the surface. Okay, and why it is having this kind of trajectory? Because this mass m is acted by external force. What is external force? Can you tell me what is external force here?
Gravity.
Gravity. So external force is constant and equal to gravity, which is equal to mg acting in the downward direction. Now, now one by one, let's think of it. This at some place it breaks into 2 parts, m1 and m minus m1. When it breaks because of explosion, has any external force acted on this?
Like the same gravity is acting, but
no, so basically, first of all, when they see, both of them are not moving together. After at time t2 or t3, what I find m1 is here, and if I m2, rest of particle is here. Why they are separated? Because of internal forces. But as it moves from here to here, has the total force acting on this, if I take these 2 as a system, has the force on this change from this point to this point?
No, sir.
No. So when is the force not changed? So basically, when I'm looking at them together, I'm not treating this as 2 objects. Let me think, if I go back to the original, how do we apply laws of motion onto these 2 particles? I apply laws of motion not onto this particle, I'm applying laws of motion onto the system. So how would this system move? So I'll take the system here. And from here, the system only force acting is mg. I give initial velocity. And I find if I take as one system, the 2 particles together, center of mass would have moved here. So these 2 positions, that's what the center mass, the concept is. If I take them as a system, even though they have different velocity and different positions, when I calculate center of mass at a particular instance, it should coincide with the center of mass of the equivalent center of mass system if the forces are equal to external. So the trajectory of center of mass single particle, and when it is broken because of internal forces, it should remain same because external forces have not changed. Okay, so let's look at what are the questions we come across in this. Something like this. I have actually a simpler version of question is mass system. Let's take a 3 mass system, and once we understand, it's a very simple process. You follow step by step, you get your answer. Okay, so 3 men A, B, C. So there are 3 men here, A, B, C. The masses are given 40 kg, 50 kg, and 60 kg. They stand in a plank which is of also mass of 90 kg. So 1 object, 2 object, 3 object, 4 object, which is kept on a smooth surface. This plank also, here the bottom surface is smooth. It's placed on a smooth surface, and sometimes they can in the water and all also. And what happens on this, A moves to C position and C moves to B. Either in C moves to position of A. If they interchange their position, an observer standing on the ground, would I find what if I change the position? How much distance will be moved? Will the B to an observer standing on the ground? So with respect to the ground, will the position of B and tank, will it shift? That's what we need to do here. So before we start analyzing, what we need to look at, if I take all four objects together as a system. So what are the external forces acting? If they are acting, if I take them together as a system, external force acting are gravity and the normal reaction. Both have vertical component. Anyway, they also become zero. That's a different matter in this case. But if I take a horizontal direction as x direction, I find on this whole system, no external force is acting. So two things here, no external for summation of x component of all external forces is equal to 0, and initial velocity of center mass also 0. Initially, all of them are at rest. So it means whatever center mass I have initially, later on also center mass will remain unchanged. So this is of that category, no change in position of center mass. So let's solve how do we do that. So we have taken a coordinate system. Let's take a coordinate system, and this coordinate system, everything is from the ground. So I have taken a coordinate system not attached to the plank. I have taken from ground, this is a coordinate system, the length and y, and the x coordinate is important. Okay, so what is initial center mass? I can easily calculate. Initial center mass will be equal to, see, these two M and plank are not moving. They are together. The center mass is together. It is a midpoint. So this is 140 into 2 plus 60 into 4 and divided by total mass is equal to 40. So that's the initial center mass position when they have not shifted. Now after this, what happened? After I taken this position, they started moving. This has moved to other direction. And it doesn't matter which order they move. It can also happen, they start moving, it takes a little more time. But finally what you find, so basically let's assume they have interchanged the position, and during this process, let's see the plank has shifted by distance. Okay, so when they interchange, the plank has shifted and the B also is shifted by distance x. So displacement on plank and B are same because B has not moved. Now, so again, I'm keeping this coordinate system same. If I again calculate center mass of this system, it should be same. Whatever axiom I have here, now I'll calculate what is center mass of this system now. The only change what has happened, earlier I applied 40 into 0, now it becomes equal to 60 into x plus 140 into plus x plus 40 into 4 plus x. We can write all those terms here. I arrive at new axiom, but this axiom and this axiom must be equal. When I equate those two, I get the value of x, the distance by which the plank will